Welcome to a new video on fault detection and control system design. So if you look at our control systems in all the videos I've done on my channel so far, they're based on linear control systems, which can be represented in a state space form like this. X dot is equal to AX plus BU, where your system matrix is A, the input matrix is B, the inputs are U, and the states are X. So if you look at fault detection, we're going to be looking at input faults here. So actuator faults, because the inputs to any engineering device are an actuator. For example, an airplane, a car. So we have something called an effective input. This can be either less than or equal to the actual input. If it is less than, it means that you have a fault present. So we can kind of restructure this input matrix B and call it BF, where BF is equal to B multiplied by the identity matrix plus the fault parameter, which ranges for each input from -1 to 0. So if we have 4 inputs, U will be 4 by 1, and then F will also be 4 by 1. So because obviously each input will have a fault to it. So now if you put this together, it means that when any of these F values are -1, it means that you have a 100% fault. So LOE stands for loss of effectiveness. If it's maximum, it means that the actuator is effective. So it means that you have a full loss of effectiveness there. If it is between -1 and 0, you have a partial loss of effectiveness. And if it is 0, it means that you have no loss of effectiveness. In other words, the actuator is fault free. And IM is the M by M identity matrix. If you look at state space in the videos I've done before, M is the number of inputs, N is the number of states, and then P is the number of outputs. So for now, we need M for M inputs. So before I actually go on to the example, I want to explain some background information. So this tutorial is actually done from my master's thesis, where I did some research under Professor Zhang at Concordia University in fault detection and diagnosis. So to do that, you have to first kind of understand what an uncertain system is. So if you have something that operates in real life, the fault is obviously uncertain, right? Like you want to know when it occurs and how big it'll be. So this you can classify into a field of engineering called uncertain control systems, where the uncertainty is bounded. So you know for sure that it'll be either a full fault or no fault. So obviously any error in a system is bounded by some values. The algorithm which we'll use is the Walcott and Zach observer. This is a simultaneous state and fault estimation tool that you can use. The parameters can be defined ahead of time to save real-time operations, so you can save a lot of time computationally, and you can implement this into systems where you don't have a lot of processing power, for example. If you look at Lyapunov theory, just a recap of it. So I haven't introduced this before, but I'll just go over it now on first time on my channel. So it's when you have a stable matrix A, all the states X will be bounded, so they will converge to some value. So it's called Lyapunov stable, and it'll converge to its equilibrium point. For example, if you drop something inside a funnel, it's going to go to the center of the funnel, right? So that's its equilibrium. So you have some principles here for the Walcott and Zach observer. You define the matrix L, A minus LC. L could also be the steady state Kalman filter gain. And you use equations 3 and 4. Q has to be positive semi-definite or positive definite. And DC is equal to PB transpose. Matrices C and B are from your system, and P and D are from your observer. So you get these and you define it. Example there, if you see UF is equal to 85%, then you have a 15% loss of effectiveness. So you estimate your states and your faults, X and U. So U gives you the fault. So the effective input is U hat, UF hat. You use L, D, epsilon, B to get these estimates. You have multiple sets of them, which correspond to the number of inputs. I is from 1 to M, and J is also from 1 to M. So if you have, let's say, 5 inputs, then you will have 5 sets of these, and you can use any one of them for your feedback, because the states are obviously for feedback, right? So our example here can be seen. We have a very simple system. You have the matrix A, so you have 3 states and 2 inputs. So you define L and Q and P and D. So the paper defined it this way, and we'll be implementing this example in Python. So let's begin. So here's the Python implementation. You can download this from the link below. You define a class for your system models A, B, C, your states X, your inputs Y, and so on. GM is the fault vector, so that's F. You define a dimension function to calculate N, M, and P, and so on. You define your simulation time steps, so X dot is equal to AX plus BU. You just do a simple matrix math there. You have to reshape the states into a vector to multiply it by the matrix A, B, and C. You can add noise to your system there, so W and V is your noise parameters. You define A, B, C, and D, your sampling time, and then you do a discretization because we'll be doing a discrete system simulation, so that has to be done. You define your initial states, your inputs, and your initial outputs, along with the initial fault vector. Inside your second function, you can have the observer there. It takes in L, D, A, B, C, U, the noisy outputs Y, your state estimates x1 hat, x2 hat, because you have two sets. So you can see for first fault, you find your first effective input, and your second fault, you find your second effective input. So you have two state estimates there, x1 hat, x2 hat. You can see how you can choose either x1 hat or x2 hat. It's up to you. They should be similar values. Your error is C times x hat minus yn. So that's your innovation, is called in control system design. Your vectors D, B, and U are from the paper itself. This one just plots everything. So this makes plots of your states, your inputs, and your outputs there. So you can put them into subplots. This is basic Python syntax, which you can get anywhere. I make multiple figures for your fault estimates, your inputs, and your states. And then I make sub-figures inside that. So I have 3 states, as you can see. I plot both the actual state along with the estimate to see what my error is. Because if you're doing anything, it's good to know beforehand what the accuracy of your observer is. So it's good practice to plot both the actual state and the estimated state. For the inputs, you can plot the actual inputs. It's a constant 2. And the effective inputs can be plotted below them. So you can compare how they behave and how the fault estimator works. So lastly, you can do the actual loss of effectiveness vector for both the inputs there. So in your simulation, I'd import the bunch of tools I need to use. I find my dimensions there and NMPR. I define my simulation time. I make empty vectors for my states and so on. I define my initial conditions. The bank of observer parameters, this goes into your fault detector, so L, Q, P, and D. And then I begin my simulation. So I just say simulate one time step, get the noisy outputs, call my observer to get the state estimates and the fault estimates too. After 7 seconds, I define a fault, 50% for U1 and 70% for U2. I have 2 inputs there at constant set to 2, that's U1 and U2. I then get my effective inputs. I then get my fault parameters there. So that's the GM hat 0 and GM hat 1. So I just divide the actual input by the effective input and divide it by the actual input plus a tolerance. So I'm just getting a percentage difference, quite simple stuff. And I bound it to -1 or 0. Then I have my norms. So that's from the paper, you can see there. So and then I put everything into my vectors which I want to make plots of. So when that's done, I can make plots. So when we log everything, you can plot the states and the inputs and the outputs. I just put them into vectors and then pass it to the plotting function after the simulation loop is over. So you just run that and then you can get the whole thing. You see how we can begin with the states, so we can begin with that. You see how you have the state estimate goes off a bit after 7 seconds because you have the fault. So when you have a fault, your state estimate will vary a bit, so that's something to keep in mind. You can see how you have a discrepancy there. It does not estimate the whole value, it goes a bit more or less depending on the input to state relationship. But that's fine because you have the fault present after 7 seconds. You can then move on to the inputs are 2, they're set to 2, but the actual inputs can be seen here. These are the effective inputs. You see how it's 1 because you have a 50% fault, and we estimate this quite accurately, as you can see there. So it's quite good. It goes from 2 to about 1, so about half, and that's our estimate. So it's quite accurate, I would say. Same with input 2, it goes from 2 to 0.6, so that's about 70% fault. So then you can estimate your fault parameters there. It's about, so yeah, it's quite close to what we actually set. 50% for input 1 and then 70% for input 2. And your estimates are about 55 and 72, so it's quite good. And we can use this information in our controller design. So that's one thing to know about fault detection. It's a very important field. And this was a basic example introducing you detecting faults and how they work and what you can do with them. So with that being said, thank you for watching. I'll see you in the next video. Bye.